We move through our cities with a deep sense of permanence. The concrete feels solid, the power grid's dependable, and we assume the systems we've built are fixed features of the planet. For the last 12,000 years, humanity has lived inside a geological epoch called the Holocene. This rare window of climatic stability provided the exact conditions needed for agriculture, urban centers, and the rise of complex civilization. But in the middle of the 20th century, that baseline shifted. We entered a period called the Great Acceleration, where human population, economic activity, and resource extraction began to surge at an exponential rate. This surge built our interconnected electrical civilization, but it also moved the Earth system into a volatile new epoch, the Anthropocene. The researcher Nick Bostrom distinguishes between two tiers of threat here. A global catastrophic risk damages human well-being on a massive worldwide scale. An existential risk is the final threshold, an event that causes full extinction or permanently destroys our potential to recover. Modern civilization is not a permanent monument. It is a fragile, temporary arrangement, resting atop planetary systems that we do not control. To see the scale of those systems, we can look at the Hunga Tonga eruption. In 2022, this single event reorganized the atmosphere so violently that it sent a pressure wave circling the entire planet. Beneath our feet, tectonic plates grind against each other for decades, storing up immense tension in absolute silence. When that resistance finally snaps, the crust slips. During the 2024 Noto earthquake, this seismic energy shoved entire sections of the peninsula 4 meters into the air. We build infrastructure on the assumption that coastlines are fixed, but in Noto, the land rose so abruptly that harbors were stranded hundreds of meters from the water they were built to serve. On geological timescales, what we confidently call land is merely a provisional draft. Moving into the atmosphere, the threats become less about sudden shocks and more about compounding stressors. Climate shifts arrive through accumulation, with heat waves drying out soil and straining grids day after day. Scientists track these global limits through the Planetary Boundaries Framework. When extreme heat and megafires align, they thin the margin of safety across multiple global systems simultaneously, from agricultural yields to the health of our forests. The Great Acceleration also introduced a boundary called novel entities. This marks the chemical saturation of the planet with plastics and synthetic compounds. These materials now act as a permanent toxic signature of human activity in the geological record. While some threats are slow, human technology has also created the means for instant ruin. A large-scale nuclear exchange would bypass every other environmental trend, instantly breaking the biosphere through atmospheric soot and radiation. This illustrates the Seneca effect, the mathematical reality that in complex systems, growth is slow and difficult, but collapse is terrifyingly rapid. If we zoom out further, we find our electrical civilization operates on the assumption of a stable relationship with our star. In 1859, the Sun released a massive cloud of magnetized plasma that struck Earth, an event known as the Carrington event. It caused auroras to appear in the tropics and induced currents so strong that telegraph operators reported their equipment catching fire. If a Carrington-class storm hit today, surging currents would flow into our grids, melting the high-voltage transformers underpinning our electrical infrastructure. Losing this electrical layer triggers the unraveling of water pumps, cold chains, and medical networks. Without power, the coordination required to sustain 8 billion people simply ceases to function. Further out, the death of a distant star poses a deeper threat. High-energy cosmic rays from a nearby supernova could strip away Earth's ozone layer, removing our primary shield against lethal solar radiation. Our only real defense against these massive cosmic events is the luxury of distance. This brings us to a final, difficult question. If a major shock breaks our global system, could humanity simply rebuild? The original rise of industry was powered by ancient sunlight stored in coal seams and metal ores that sat right at the surface. These resources were accessible enough to be extracted with muscle and basic tools. Early oil fields pushed toward the surface under their own pressure, but we have already consumed that low-hanging fruit. Today, the remaining oil and minerals lie deep underground or beneath the ocean floor. Accessing them requires the very machines, supply chains, and high-energy industry that a collapse would destroy. Even solar panels and wind turbines are products of advanced industrial chemistry. They cannot be used to restart a society that has lost the ability to manufacture them. The thermodynamic ladder of easy energy has been pulled up behind us. A fallen civilization lacks the accessible resources to ever climb back to where we are now. This leads us to the Great Filter, the hypothesis that a barrier exists which prevents complex life from enduring. We must consider if the transition from the stable Holocene to a self-endangering Anthropocene is that barrier. Recognizing this fragility should not inspire panic, but a profound, practical gratitude. Our survival relies on the silent, generous cooperation of rock, water, climate, and a reasonably calm star. The universe never promised us stability. Our civilization is an improbable, temporary experiment, and it will endure only if we respect the systems that allow it to exist.